Okay, so what are my lambdas? -3 and -8. Notice that this matrix is non-defective, by the way. There's no repeated eigenvalue, so it's already a guarantee that it's non-defective. But that's not what we're being asked about. We have these two eigenvalues, so we have to find the corresponding eigenvectors now, right? So as usual, we just go through it one by one. If I take -3, I need the null space of, for lambda equals -3, I'm going to add 3 to the main diagonal of the matrix. That's going to give me -3 and 1, and 6 and -2. That matrix has to be not invertible. Can somebody give me a vector that would work for that null space? 1 and 3, okay? You just swap, you pick whichever row you want, and swap the two numbers and change the sign of one of them. Okay? So we get 1 and 3, very good. And then the other eigenvalue is -8. So when lambda is -8, we take the null space of what we get by adding 8 to the main diagonal. So that's going to give me 2 and 1 and 6 and 3. Okay. Can somebody give me a vector that we could use for that eigenvalue? Go ahead. -1 and 2. Looks good to me. Okay? Perfect. So actually, if we wanted, we could write down the general solution. I'm just going to do that, even though that's not required here. The general solution is just C1 e to the -3t times 1, 3 plus C2 times e to the -8t times -1, 2. So it's just this expression right there. That's the general solution. But now I want to try and draw the picture. Try and draw the phase portrait. So the phase portrait is where we put down our axes here. I'm going to draw a picture for you guys. Okay, so draw a picture. Put down the axes. Remember that this vector x of t, consists of a top line and a bottom line, right? There's a top row and a bottom row. So if you look, for example, at this solution or at this solution, there's a top entry and a bottom entry, a top function and a bottom function. And just recall, guys, that the top function, if I call this x of t, the top function is usually just x1, and the bottom function is x2. And those are two scalar functions, no arrow on top, right? Two scalar functions that make up this whole vector, x of t. And I like to label my axes correspondingly with x1 and x2, like that. So the way that you do the phase portrait, it's very simple. You really just, you draw the eigenvectors that you found there. So we found the vector 1, 3. Put down 1, 2, 3. And you just draw that line. Remember that? We would end up with a straight line. And as basically at time 0, your particle is going to be either there or the corresponding point down here. It just depends on if the constant in front is positive or negative. What happens to the particle that is obeying this differential equation as time goes forward? It moves along this line, but which direction? How does it move along the line?
Into the origin.
Towards the origin. Why is that, Justin?
Because it's a negative exponent.
Exactly. E to the -3t. See, we're really looking at this first solution that I circled right over here. E to the -3t times 1, 3. So as t gets bigger, your exponential term is approaching 0. It's sort of damping down the effect of the vector 1, 3. So what happens is you need to put arrows on this. The arrows are coming towards the center. Okay? Make sense? The other eigenvector is -1, 2. Well, that would be this direction right here. So I just draw a straight line through there. It doesn't have to be perfect, by the way. I don't need a perfect picture. It's a rough sketch. And which way are the arrows pointing on those two lines? Also towards the origin, right? Because you have a -8 8 on the exponent. And so this is called a sink, exactly. Both of my lambdas were negative. It means every single direction that you approach from is heading straight towards the origin. So there are other lines that you can draw, and they are all coming towards the origin. You can just draw them all in here. There's no requirement on sort of how many things you draw, but in every direction, no matter where you start, you see as t gets big, look at this thing in the box here. As t gets big, it does not matter what C1 and C2 are. It could be any one of those different curves. Does not matter. Everything is going to die off to the origin. Because when t gets big, e to the negative 3t is getting killed to 0, and e to the negative 8t is getting killed to 0. Does that make sense? Okay, so this is a sink. That's what we call the sink. Okay, I promised to do an example where we have complex numbers. So let me show you another example now. Another example. So I found one in the book kind of on the fly here. Hopefully it's going to turn out nice. Okay, so let's do the same thing. Do the same thing for I'm just going to write down the matrix. The matrix A is going to be 3, 13, negative 1, negative 3. Try it for that matrix. Okay? So let's do our usual thing. Let's take the determinant of what we get when we subtract lambda from the main diagonal. Okay? And so this is going to be 3 minus lambda times negative 3 minus lambda plus 13. And if I expand that out, lambda times lambda is lambda squared. And then I have minus 3 lambda and plus 3 lambda, which cancels out, right? To 0. So then I get minus 9 plus 13 is plus 4. Oh shoot, this isn't the best example. I was hoping, okay. Anyway, well, this will be okay. All right, so in this case, does anybody know what my lambdas are? Plus and minus 2i. Okay. So let's find the eigenvectors. Okay. So we'll find the eigenvectors. So that means we've got to do the null space. We're going to use only the positive one. So we'll use 2i, and we're going to take the null space of the matrix that we get by subtracting 2i from the main diagonal. So this will be 3 minus 2i, 13, negative 1, and negative 3 minus 2i. This is where it's oh so important to remember that these rows have to be multiples of each other, so you can cross one of them off. I always like to cross off the one with the worst numbers. So we'll use the second row only, and then we can put down our vector. What vector would you suggest that I use here?
3 plus 2i.
Go ahead.
3 plus 2i and negative 1.
3 plus 2i, so you swap it out and change the sign, and then leave negative 1 the way it was. That was good to me. Okay. Which we can decompose. We may as well do it now. Can somebody tell me how does that decompose into a real piece and an imaginary piece? 3 and negative 1 on the first entry, and then 2 and 0 on the second entry. Everybody with me? Okay, so now I can start solving it out. Let's start solving it out here. So our solution for x of t is going to be e to the lambda t, so that would be 2it, times the vector, which we've already split up, is 3, negative 1, plus I times 2, 0. Okay? And this exponential piece, of course, what am I going to do with that? Write it in terms of, right, Euler's formula, which decomposes it with sines and cosines. Very good. So this is just cosine of 2t plus I times sine of 2t. Okay? Times the vector 3, negative 1, plus I times the vector 2, 0. Okay? So we're getting some good practice with complex numbers here today. Okay, so I'm going to just FOIL it out like we've been doing. That means I'm going to take the first and the first, so that would be cosine of 2t times 3, negative 1, and then minus sine of 2t times 2, 0. That's the first piece. Agreed? And then the second part is plus I times, let's see, it's going to be cosine of 2t times 2, 0 plus sine of 2t times 3, negative 1. Make sense? So now this one right here, this is going to end up being my x1, my first solution. And just this part right here, without the I, is going to be my x2. So you see how I'm getting my two solutions?
Can you do that on the test? Say that's I1, that's I2.
X1 and x2?
Yeah, like.
Yeah, although be very careful. That's starting to get dangerous because if I can't tell, if you do that, the I can't be in it. So I would not recommend that, quite frankly. I would just suggest, actually, so then the general solution, I would just suggest you come in and you write C1 times, of course you could just say X1 plus C2 times X2. Maybe for right now, I think I want to do that because we're spending a lot of time here and I want to get on to some other things. But anyway, so this is the format of it, your general solution. Okay? Everybody all right with that? Now, let's suppose that I wanted to graph the phase portrait for this. I'm going to go ahead and I don't need any of this anymore. The phase portrait for this system. Okay. So the way we usually would do this is we would draw some different curves, right? So one of the options would be to just choose C1 to be 1 and C2 to be 0, and that would mean that we're just going to graph this. Okay? The only thing I really want you to realize about this is that, well, of course, at time 0, the particle starts at 3, negative 1. It's going to start right there, okay, for this first solution. The key thing to keep in mind about this is that as you run through every 2 pi units, sine and cosine return to wherever they were before. So if the particle is right here at time 0, it's also here at time 2 pi. It's also here at time 4 pi. It's just basically, well, actually, there's a factor of 2 in front of here as well. So it's actually every pi units. Every pi units of time is going to be there. And when you're halfway back to that point again, you're going to have, basically, this is going to be minus of this, right? So in other words, when t is pi over 2, right, then you just get negative of this, which is negative 3, 1. Okay, so this is t equals 0 or pi or 2 pi, the particle will be here. And over here, it's going to be at this point at, half of pi or 3/2 of pi, and so on. Make some sense?
So you just set C1 to 2 to 1 or 0 to 1?
Yeah, what I'm doing right now is setting C1 to 1 and C2 to 0. You get this picture? Right? And the idea is basically that this forms a closed loop. It actually forms a circle. I don't know the details of the circle. I don't want to get into that. But it forms a circle.
You have to say what directions going?
Pardon?
You guys see what?
No, don't worry about the directions on it, because you can determine what the directions are, but it takes a little more analysis, and I haven't really explained that in class. So basically, this pair of eigenvalues is giving you a circle. Circles. So for each choice of C1 and C2, you're going to get circles, right? That's basically what you're going to get. If you take C1 equal to 1/10 and C2 is 0, you're just going to get basically the same circle shrunk down by a factor of 1/10. So you're going to get just a bunch of different circles. I can't, and they're not perfect circles either. They could be ovals, right? So I don't want to get too wrapped up in that. Now, if the eigenvalues had a real part to them, see, there's no real part here. If there had been a real part, then when you write down your solution over here, what's going to be different? There'll be an exponential, won't there? So then you're not actually going to get a circle. What you're going to get in that case is a spiral, either out or inward, right? It's going to be like a circle, but its distance away from the origin is going to be either expanding or shrinking. So you can get a spiral in, or you can get a spiral out, depending on whether it's e to the positive t or e to the negative t times the e to the bit, which is the imaginary part. So this is like e to the at versus e to the negative at. Kind of makes sense, roughly?
You see us more giving us one like the line.
Well, I've certainly gone over that more.
Right.
Yeah. And if I gave you one like this, it would be that I was, not expecting you to know a lot in advance, and it was somehow I was going to give it to you in a way that I thought you should be able to figure it out on the spot. But yeah, more than likely, since I haven't really gone over this, I may go over this next week and then have a little higher expectations on the final. But at least for now, I haven't done too much with that. Because yeah, you can have a saddle, you can have a source, you can have a sink, and now you find out you can also have a circle, you can have a spiral in, or you can have a spiral out. There's actually a lot of choices. Okay. And all of that is just for non-defective phase portraits, right? And we haven't even talked about defective matrices yet. So, okay. I think I'm going to leave it at that. Are we good so far? Now, I haven't gone over anything yet. Oh my goodness. I haven't gone over anything on the chapter 6 stuff. So I'm just going to keep plugging away. Actually, I'm going to keep plugging away. If you got to go, you've got to go. That's all right. I have to be somewhere at 6, so this isn't going to go on forever. But I'm going to go a little further into problems 6, 7, and 8 on this sheet, which all have to do with the material from chapter 6. Okay? We've done quite a bit with eigenvalues and eigenvectors. We've done quite a bit on these systems. But what I haven't talked at all about is chapter 6. So let's do that. So here's the first one. I'm going to do number 7 first. So I can show you a variety of problems quickly. What it says is, let L equal negative d squared plus 2d minus 1. And what I want us to do is answer the following question. Is x e to the x an element of the kernel